No, no problem.
All right, that's good. I mean, if you notice something like this, the recording was not on. So yeah, luckily all the things that I talked about were just recaps of previous ones. But now we go to theorem 2.3. So this gives an example of the situations where we have just real numbers, and the convex sets are exactly the intervals in the real number line. So what it means basically is that when you go along the line, if you think about the intuition I just mentioned, or the intuition we talked about in terms of the convex sets, is that there's just one line segment, you know, the one line from which you take segments of the real number line. If you think about that and you move along the line, if ever you encounter a point that is not inside the set, then the set is not convex. Well, obviously, let me just rephrase that. I rephrased that a little bit badly. If you are inside the set and you move along the line, then whenever you go outside the set, then if you go further along the line, you will never ever encounter more points of that set again, regardless of what directions you go to. So it has just two end points, this set. You can think of it in this way. And everything between them is in that, and everything outside that is outside the set. So exactly those that are the intervals. Obviously, the interval can stretch to infinity in one direction or the other. And the set as a whole, the all real numbers inside itself, it's of course convex. Here's the proof. I'm not going to go through this proof. I really do urge you to, if you have a hard time understanding what makes convexity so compelling, I really urge you guys to go through this proof and try and understand it. I'm not going to use a lot of time on these proofs that are of auxiliary importance, but the approach is, it's a very, I'm looking for the word in English. Well, it's very illuminating in the sense that if you want to understand why this theorem holds and how the idea of convexity interplays in this simple case with the fact that we are only dealing with real numbers, then this proof is very helpful. And I should really recommend that you read it. There are these four different cases: when there's a finite interval, when there is a on one-sided infinite interval, and then when both sides are infinite, and then obviously any line segment is inside that. So this is the intuition about convex sets, and really the thing you need to take away from this is the definition of convexity. That is the important takeaway from this 2.1. This definition 2.1. That's the important thing from this first part of chapter 2. We will move on to convex functions now shortly. Before we do, we'll do a little bit of a warm up, just a little bit warm up so that we get on track on how this is going to go. I'm going to pause the record. And next, I will mention convex functions. So convex functions is are functions that have some properties pertaining to or connected to the idea of convex sets. And convex functions are nice because they can be used to define convex sets. So when we use convex functions as our constraint functions, then if the constraints are of a suitable format, then the resulting set that satisfies these constraints is going to be convex. And that's the importance of convex functions. We will later, at the end part of this course, I will show you that in fact there is a not quite as restrictive definition for functions which can then be used to define convex sets. So even though convex functions are by necessity, when you use convex functions as constraint functions, you know that you are going to get convex sets. The converse is not true. you can get convex sets with functions that are not convex. But we'll talk about that towards the end of this course, so not at this stage yet. So we define, here's a part in this section, what is the important concept here is this definition 2.4. We say that if we have we start with a convex set, usually we just say that we think that this function is defined on a convex set. So it's defined on a set whenever the values come from the set K, and this K is itself convex. Very often, but not always, the case is that this K is the whole set X, the whole space X. So X is now our placeholder for whatever the space our variable values comes from, and these would be vectors usually, and real number vectors or complex vectors, don't know yet at this point, but any vector space that we deal with, and K is a subset of it, which is convex, but it may be also the whole set X because that is convex too, or some subset of it, subspace of X is also convex, but it can also be like let's say it's a unit sphere, you know, the unit ball and all the points inside it, or a square or a hypercube or something like this, as long as it's convex, this set over which we are defining this function. Now, we say that it is convex. So this function maps the values from K to real numbers. And we say this function is convex if we take 2 points from K, like in my previous example, if I have this set, let's say it's this circle here, and there take 2 points on that, and the function has some value at this point and some other value at this point. And then when I calculate its value along this line, then the value of the function at that point is less than or equal to, if you take the values at the endpoints and calculate the convex combination of the endpoint values. So what does it mean? It's very hard to give an intuition about this as in terms of higher dimensions, but I can give you a picture or in one-dimensional case. The two-dimensional case could be drawn, but I'm bad at drawing. We'll see in the MATLAB exercises when we do those MATLAB, we can draw pictures of convex functions, graphs from 2 dimensions to 1 dimension. If you have from R3 or higher dimensions to real numbers, then it's very, very hard to visualize it. But for one-dimensional case, when we have real numbers to real numbers, then a convex function will look something like this. And what does the definition say? It says that if I take 2 points here, X and Y, thusly, so here's X and here's Y, and I draw a line between those 2 points, F, at the points where F of X, I'm going to use red color now. So if I draw a line, a straight line from over here, then the function is always below this straight line, or it can touch it, but it must be below or at that straight line. So it has the same flavor to it as convex sets, that the function, when it curves, it kind of curves. If you think about, let's say, if you think about this, if we think about this region as being the region where this function sets a limit, and we're thinking about this region here, this on the upper right side of this curve, if that is our region of interest, and we are using this function here as a limiter, so it has to be above this curve, then that set is convex in here, in this case. So the intuition comes from that. But it is expressed in such a way that the function's value at the points between X and Y is less than or equal to the point that you get when you draw a straight line from xfx to yfy. So I hope this clarifies what 2.2 means. And we say that it is strictly convex if it remains below that straight line. So if we think in terms of what is intuitively, obviously, you know, there may be pathological exceptions to this, but if you think about convex versus strictly convex, then strictly convex means that, okay, the function is convex and it's not a straight line. A straight line will give you a convex function, but if there is curvature, then the curvature is like this, and the curvature being going, you know, like this downwards, it does have curvature. It's not straight. Then it's strictly convex. And the opposite of convex is concave. When it bulges upward, you know, the function bulges upward, it's concave. So the only functions that are both convex and concave are those that are straight line, and then neither is strictly convex nor strictly concave because they are on a straight line. So I hope this gives you an idea of how convexity works when we're talking about functions. But in 2 dimensions, it's still pretty easy to think about it. So if we think of the z-axis or the up-down axis as the value of the function, and then we are moving along a plane, then it forms a kind of cup, this function, the graph of the function. But in higher dimensions, obviously, the graphical and geometric intuition is very hard to get. You can come up with some intuition, for instance, like if we have let's say that we have a temperature gradient or temperature field, like we are in a space and there is temperature inside that space, then the temperature value of different points can be convex, in the sense that if you take temperature here and temperature there, and then when you move along the line, you know, in the space, then the temperature is less than or equal to the convex combination of these 2 points. It's hard to give a graphical intuition about what goes on here, but algebraically, the intuition is that if you go from one place to another and you're monitoring that value of that function, even in higher dimensions, what happens is that it can only change direction from increasing to decreasing once. Sorry, from decreasing to increasing once. So it can be decreasing while you are going in that direction, but if it ever changes to increasing, it will then keep on increasing. It will not go up and down and up again. That's the idea here. So play around with this concept and try to think of it in these terms. It's helpful to think about graphs like this, where it just, you know, goes down but it's also helpful to draw think in 2 dimensions, try to get an idea, and then again think about this in terms of for instance temperature or some other concept that appears in the space, maybe pressure. It could be pressure. Is pressure in a container, is it convex? I don't know. Think about it. Is it? Some other fields, vector fields of the magnitude of a vector field or something like this. What would be wind speed from one point to another in a constrained region, something like this. These might or might not be convex, depending on how the function that describes the behavior of that measure that you are measuring at each point in space. When we get to even higher dimensions, obviously there is no geometric intuition that you can derive. So you have to rely on trusting the algebraic intuition between this, so that whenever you draw a line, even in higher dimensions, between one point and the next, then if you take the convex combination of the values in there, then the value values on the line will remain below that, regardless of 2 points. Again, this is somewhat hard to grasp directly, but when you play around with this concept a little bit, it should open up in your mind eventually. Here are some examples. If we have X, any linear, when I say linear space, I mean space, usually I mean just vector space. If we have a vector space and we have a linear function, we'll shortly do a visit to Appendix A to revise on what linear functions are. And we have a constant C, that is a real number, and we define an affine function, which is g of x plus c, so it has a linear part and a fixed part. Then f is both convex and concave, because the value of the function at the convex combination on the line segment can be obtained as a convex combination of the values at the endpoints of the line segment. So that's really important. What linearity breeds is obviously convexity and an obvious equality of the equation, or the inequality 2.2. It becomes an equation when we're dealing with linear or affine functions. And that's really the power of linear and affine functions comes from the fact that it makes the inequality 2.2 an equality. So any and all things that we can do with convex functions, we can do with linear functions, and then some, and more so, because it gives us a specific class of optimization problems, meaning the linear problems. They're relatively easy to solve because of these properties. So if we have the value of the function at 2 points, and the value of the function of the cost function is different at these 2 points, if the function is linear or affine, then it is the minimum of the line segment that joins these 2 points is at either ends, at that end where the function is smaller. So it just keeps on getting smaller. Whereas if the function is convex, but not linear, I mean strictly convex, then the minimum might be obtained somewhere between them. That's also something that you understand why convexity and why convex functions are, why this concept of convexity is important. If you have these functions that are neither convex or concave, then those functions, we could call them non-concave or non-convex functions, but a more intuitive, albeit maybe a little bit misleading or exaggerating concept that we could use are squiggly functions, functions that go up and down a lot, more than once. So that could be something that you can derive intuition from. We'll look at some examples both in this lecture part and also in the exercises. Here's an example. We have an interval of real numbers, and we show that this function f of x, which is defined as x squared, is strictly convex. And we can define it in such a way that we calculate the value of it in 2 points, x and y. And understand that x minus y squared is obviously greater than 0 if x and y are different, obviously, because the square of any real number other than 0 is greater than 0. That means that if you take x minus y squared, it's x squared plus y squared plus 2xy. And this implies that 2xy is always strictly smaller than x squared plus y squared when both x and y are different, when x and y are different. Obviously, they're both different if one of them is different from the other. Sorry. I sometimes make these slips of tongue where I add extra words, like saying they're both different. Obviously, they are both different from one another. So here, the algebra is pretty straightforward. We just calculate the square of lambda x plus 1 minus lambda y. And at some point, we we don't even have to make use of the fact that lambda is between 0 and 1. Well, it is used somewhere in here. Let's see where it is used. It's used on when you are transitioning from one line to another. The last part, you are using it there where you can make, let's see. No, it's never used anywhere in there. The fact that lambda is between 0 and 1. Yeah. So that's neat. So we know that the convex combination of x, lambda x plus 1 minus lambda y, when you take f of that, then that is smaller than lambda of f of x plus 1 minus lambda times f of y when f of x is equal to x squared. In general, we will not be using this kind of deduction to prove a function is convex. Instead, we will be using some of the following theorems. So we have some functions that we know to be convex, like linear and affine functions. We will show that given we can deduce the convexity of a function from certain aspects of its first and second derivative, mainly the second derivative. If we can deduce if we can calculate the second derivative of a function, then we can deduce its convexity in some region. Now, of course, all functions are differentiable, but when they are, then this is something we can do. Most of the functions we will deal with are differentiable functions, so we have that's nice. So here's some theorems about that. Theorem 2.7. This is of less importance, but the most important is definition 2.4, obviously. But theorem 2.7 is highly important from the point of view of applying and recognizing convex functions when we deal with convex optimization problems, or to recognize when they're not convex. This is more in the line of recognizing when things are convex. The non-convexity is a bit trickier, but proving convexity, let's focus on that first. So we have two vector spaces, x and y. We have a convex set over x, and we have some interval of real numbers, and then we will be defining things. So for instance, if we take a positive linear combination, so this A says, if we take a positive linear combination of convex functions, then what we get is a convex function. And by positive linear combination, I mean we take f of I, where I is 1 of 1 to n, which is convex, multiply it with a coefficient alpha, which is positive, and then we add alpha I mean, multiply with alpha I, and we add all of these alpha I, fi combinations, we add them together, we get a function which then is convex. So positive, and I must stress the fact that this needs to be a positive linear combinations. If we if we multiply them with negative numbers, then the result is not necessarily true. In general, it's not. Also, if we have a family of convex functions, then defining the function as the maximum of these convex functions at each point, and that is also convex. So understand that this f at x is, you look at the values of these different fi's and pick the value that is the largest, the maximum of them in this point. The result is convex. I'm going to give you an example, a graphical example here, draw a picture for you. I'm going to use this paper. So let me give an example. I draw here two functions that are supposedly convex in real numbers. So here are two functions, the graphs of two functions that are convex. So if I take the maximum of these, then the graph of that will consist of it consists of this V shape here, and we see that this is also convex. I mean, that's a convex part, and then it shoots up there, but this is convex from then onward. It's going to be convex. We'll look at the proof of that in later exercises. If we have a decreasing function, which is convex, and we have a concave function, then the composite function is convex. I'm not going to go through all of these now. I'm going to stop here, and we're going to visit Appendix A, because we're going to be getting a lot of new concepts here, a lot of theorems. So don't worry about the fact that this may be going over your head at this point. If we have an increasing convex function and a convex function, then their composite function is convex. So you have to understand that decreasing and convex and increasing and convex functions, they work in terms of composite functions. They result in somewhat different behavior. We'll explain that, why that is. It's because when you are using if you're using an increasing function, then that preserves the order of elements. If you use a decreasing function, then it reverses the order of elements. So you take f of x and f of y. If x is smaller than y and f is increasing, then f of x is smaller than f of y. But if f is decreasing and x is smaller than y, then f of x is larger than f of y, right? So that's why C and D behave as they do. And E part here says applying an affine function and a convex function, then if you take the composite of those, then the resulting function is convex. Also, if you have F is the money shot here, basically. Is that if you have a function that is convex, defined over a convex set, and you have some C, which is a real number, and you define the set E as such x's for which f of x is smaller than or equal to C, then the resulting set is convex. And this F is the important part here. So you take the x's such that f of x is smaller than C, then the resulting set is convex. It's hard to explain this in higher dimensions using a picture, but in 2 dimensions, or 1 dimension really, in 1 dimension, it simply means, remember that convex sets in real numbers are just intervals. It means that if we set the limit for values, if we set the limit like this, we look at values of x such that f of x is smaller than C, then it results in an interval between this point and this point. And this is what happens if you have convex functions and you restrict your x's to the places where the convex function has value smaller than or equal to some constant, and you draw a line like this, then it will result in an interval in this region. In higher dimensions, it's a little bit harder to get a graphical intuition, but it works in a similar way. Right. So shortly, we will talk about differentiable functions and convex functions. And I'm going to pause the recording for a little. It doesn't matter. So like I said, the range and null space are important concepts that you should have probably learned. We're not going to be using them a lot here. We sometimes may mention that there's a null space there and so forth. It means that those objects those elements of your vector space, which would map then to 0. And like I said, this linearity concept here is really important. We're going to be using it shortly. Think matrix multiplication, and when we're going to be talking about the derivative, then it can also, you can think of it as the inner product of a given vector. So if you have a Rn to R function, so a function with n variables that maps to real numbers, then its derivative comes in the form of what we know as the gradient. So you take the partial derivatives of each of these variables with respect to each of these variables of the function, and then you form a vector from that. And then you get that vector, it gets a value at each point, and then you take the dot product with that, with some vector, you get a real number. So you can think of a derivative of a Rn to R function. You can think the derivative of that as a linear functional, and we'll be doing that shortly. We'll get to that, how we do that. Another important concept is what is known as a bilinear mapping. A bilinear mapping, basically, it comes from two different spaces at the same time, and it maps to a third space. So you take two elements, one from space X, one from space Y. You calculate a function whose value depends on X and Y, and you get a value that goes into space Z. Again, this is probably easiest to think that we are mostly only going to be using this in the case where Z is the set of real numbers and X and Y are the same space, but we are going to be using a matrix, and we're going to be multiplying the matrix from both left and the right from with a vector. So your matrix is a matrix A, and then you have X transpose A times X, and that's your bilinear. Sorry, X transpose A times Y. So you have two parameters, X and Y, and then the function, the linear bilinear mapping, is then the function you get by multiplying the matrix A from the left with X and from the right with Y. And let's just forget the sesquilinear and whatever's. You can forget about that. Symmetricity, yeah, so that B multiplied with XY, XAY and YAX are the same for every X and Y. Could be, could be not. This depends, of course, on the matrix. Like I said, in general, these may not be matrices when we're dealing with higher dimensions, but mostly when we talk about optimization problems, we are going to be talking about Rn, and the more abstract spaces, we leave that for more advanced material. But I still want you guys to be able to think in the abstract terms here. And I'm going to give some examples of more abstract situations, which may or may not be helpful to you. So bilinearity basically means that it is linear in both of its arguments. So if you take B of alpha X plus beta Y and Z, you get alpha times Bx of Z plus beta times a B of Y and Z. So, you know, both arguments separately can be broken down into linear. And you can double check that multiplying a matrix from both sides with different vectors is in fact a linear, bilinear, results in a bilinear operation. So here are some definitions that we're going to be using. I'm not going to go to matrix representations. You can go through this, and it explains you how matrices can be used to represent linear operators. It's fascinating, and it's good read, but we're not going. This is appendix, so this is something that I hope that you will take your time to read if you are not intimately familiar with this. And then with bilinear mappings, we can define it as having properties. Positive definiteness means that if you take a non-zero vector x, if it's a symmetric bilinear form, then it's positive definite if b of x and x is always greater than 0 if x is non-zero. And positive semi-definite just means that b of x and x is never negative. And the same for negative definite and negative semi-definite. We're going to be using this. Okay. So I took this time to explain to you what are linear and bilinear mappings. It's really important to understand the difference of the two and what we're going to be using them with. And I'm going to spoil it to you. So linear mappings, mostly we will be using a linear mapping as a linear functional that comes from a dot product with a fixed vector, and you take a dot product with another vector. What you get is or the inner product with another vector. What you get is a linear functional, basically. And bilinear mappings will mostly take the form of a matrix, and you're multiplying the matrix from the left and the right at the same time with different vectors, and what you get, again, is a real number. And these will take the place of the first and second derivative respectively in vector valued spaces, right? Sorry, in vector spaces with real valued functions. All right. So these two things, concepts of linear mappings, again, going to pause this a little while shortly. I'm now resuming the recording. We just talked about these linear and bilinear mappings. I'm going to skip the part about limits and continuity. I'm going to assume that it is familiar to you. If you remember the epsilon, delta, and all that sort of stuff, check it out. It can be found at this part A 2.2. I'm going to very quickly show you what bounded linear operations mean. We say that the linear operator is bounded if there's a constant such that if you take the linear operator A of x, and you know what you get is usually a vector, and we assume that these spaces are normed spaces, which usually in vector spaces it just means the regular norm, the Euclidean norm, but it can mean something else. You should revise and go back to what norm means, but you can think of it as the regular Euclidean norm for most situations. We can define the norm of a linear operator as going through all the vectors that are of length 1 or norm 1 and taking the largest of those and applying AX to that and seeing which of these resulting vectors has the largest norm in that others in the target space Y. So basically, when I said that linear operators conform to correspond to matrices, then what you can do is matrix multiplication does to a vector is it rotates and scales it. That's the only thing that it does. It turns it into some other direction possibly, and then changes the length. So when you multiply a vector with a matrix, you get a vector that points in another direction and may be shortened or becomes longer. Now, of course, when we're dealing with different spaces, then this may happen that you lose some dimensions, like R3 vector becomes an R2 vector. So a vector from 3-dimensional space becomes a vector in 2-dimensional space. But never mind that. You can think of this as the norm of the matrix is the largest vector elongation that you can get from a unit vector. You know, go through all the unit vectors and pick the one that becomes scaled the most. And that's your norm of the linear operator. And the linear operator is bounded if it has a norm. finite norm, obviously. And we call this the operator norm. And, you know, we're not going to be needing this a lot, but I'm going to mention it here because there's some theory here, and you know, you can talk about these, look at these normed operators, boundedness, continuity, and continuity at zero, and so forth. And the thing is that linear operators are very predictable in the sense that if they're continuous, they're bounded, and vice versa. Not going to go into this that much. What I want to go through here is differential calculus. And again, here, I'm assuming you have some background in it, but just as a revision of those concepts or raising the abstraction level a little bit, I'm going to mention some ways of defining a derivative. So I don't know if how much and how you've in the previous courses, how you were defining the derivative. Probably in many courses of univariate, so functions of one variable, you define it as the limit of f of x plus h minus f of x divided by h as h goes to 0, right? That quotient of the change of your parameter and the change of the function. Well, the quotient of the change of the function with respect to the change of the parameter. So like if you make an infinitesimal change, how much does the function change? Well, in vector calculus and in higher dimensional, more abstract spaces, the differentiability or derivative is basically the same thing. So the first thing we define is what is called the Frechet Frechet derivative. And this looks bad, but I really do think that you should look at definition B1 and learn it, if necessary, by heart. So drop the level of abstraction to the point where you feel comfortable. But if this maps a function, maps x to y, and we're taking G, which is an open set, it can be the whole space X, but you know, as long as there are no hard limits, then this definition works fine. So we say that it's differentiable when if we move from one point to an X. So I'm going to stress this definition. Look at B1. So this means that our function f has some value at point X. It's really hard to draw. I don't want to draw a picture because I don't have, I don't want this to be too graphical as an intuition, but I'm going to wave my hands a little bit. So we are at a point, and this point can be in some very abstract space. And think about that's at the tip of my finger. We are at this point. That's my X. And the value of f is f of x at that point. So that value of f of x resides in some other space. It's over there somewhere. I mean, don't know what it is. It's a vector, something that looks like this, some in other space. And now we move from x a little bit in some direction. So we move in that direction or that direction of this h. H is now a vector. It's a little tiny, teeny vector, and we move from this place, this x a little bit. And we look at what happens to the value of f of x. So if this is differentiable, and we say Frechet differentiable, but differentiability, you can think of this as being differentiable. And if you look at this definition, and what happens is you have your original, that's your vector. This is the result of f of x. That's your f of x here. You move in that side from x a little bit, namely, you know, this much. Let's say this is my h, I move. So what happens here is that I can get this same result plus then some linear operator that operates on h, just linear, just a little linear perturbation from this edge, this end here, and then plus something that we call the remainder term, and the latter part, the third part here, this norm of h times r of xh is it like a disturbation? It's an approximation error, if you will. So this f of x plus ax, meaning that this linear operator a, what linear operator it is depends on x. And we take that linear functional, if you want, if this is if y is the set of real numbers, and we move in a linear fashion based on what h is. And then there is a slight approximation error that is now I'm forgetting the English word again. That is proportional to the norm of h. So how far h's norm is basically how far we go away from x. So it's proportional to the norm of h. And then there is some remainder term that when h goes to 0, then the remainder goes to 0 as well. So the approximation error goes to 0 at least the quadratic phase. I mean, I'm not going to say at least the quadratic. It goes super linearly. It goes faster. It goes to 0 faster than the norm of h. That's what it's supposed to say. And if you then rearrange these terms a little bit, then what you get from this differentiability, if you take the, let's call this a, the f prime at h. It's like the derivative of x at a, f prime at x, sorry, not h. Then it follows that if you take the right-hand side where there's f of x, and then there is this f prime of x operating on h. Remember now it's a linear operator. And you subtract this from f of x plus h. That's this in this limit characterization here, the numerator, we have the value of f at x plus h minus then the part that comes from f of x plus f prime of x time operating on h. That's your approximation. So f of x plus f prime of x h is the linear approximation of the small perturbation at h. And you take the norm of that. That's actually then going to be the error term. That's the norm of h times r of x and h. Then as h goes to 0, then this goes to 0. And we can't really say that this f prime of x is the limit as of f of x plus h minus f of x divided by h, because we can't divide with vectors, right? But we know that this is as close as you can get to the quotient definition of derivatives. So if these were real numbers, now let's drop this level of abstraction heavily and think that this x is the real numbers and y is the set of real numbers. Then we can dispense from this. We can say that when this is true, we can, for instance, first of all, we can throw away the norm itself. We can divide the h there, and we can get the characterization that f prime of x is equal to the limit as h goes to 0, f of x plus h minus f of x over h, which is the classical definition in univariate case of the derivative. But obviously, because we're not dealing with real numbers, we're dealing with more abstract concepts, then what we're really looking for is the linear operator that is f prime of x. So it's not a value. The derivative doesn't have a real number value, even though the function itself gets real values. Instead, it's a linear functional from the original space to the real numbers. In this case, if we just drop the level of abstraction in such a way that y is the set of real numbers, we're dealing with vector space that maps to real numbers. We take the derivative, then the derivative is now a linear operator from here to there. And how do you express a linear operator from Rn, or a linear functional from Rn to R? Is basically you take a vector and then your parameter vector, you take the dot product of those, and then what you get is a real number, right? So we'll do an exercise of this later on. This vector that we use in this dot product when we're dealing from Rn to R, this derivative, if you will, is known as the gradient. So if you know how to calculate the gradient, you can calculate this derivative in the case of from Rn to R. Strictly speaking, by this definition, the gradient itself, which is a vector, is not really the derivative. Instead, the derivative is a function in which you take the dot product of the gradient and whatever is the age that you put in there, and that's actually, and it tells you the minor change in the value of the function when you move h from x. So you're at x and you take a small step of vector h, then take the gradient at point x, take the dot product with h, and that tells you roughly how much does the function change when you go in that direction. There is another term, another derivative. So this is a Frechet derivative. This is like the derivative, if you want to think about it this way. Not going to go through these theorems. I want you guys to revise this and look at these examples and so forth and understand this. If you have a real numbers to something else function, then this derivative can be defined in the old school classical way. Here you can go through these examples, and I really do urge you to study these and get an intuition about how the Frechet derivative works. Also, I'm not going to go through this in great detail at this point. We're going to be not needing these more abstract theorems, but I do really urge you to study this a little bit. And there are all these definitions for the chain rule and differentiability of composites and so forth. Not going to touch that now. A related concept, which can be then derived directly from there. We can derive the derivative as before, using the quotient and the limit. But in this case, before we can do this, we have to decide the direction into which we are going. So then we get what is known as the directional derivative. So if we take the directional derivative is that we have a function, we are at a point, and we want to know the directional derivative of the function in some direction. Then we can use this quotient limit like we do with univariate case. And in this case, we simply take the direction u, we move by a factor of t in that direction. We look at the change in this function, so f at x plus tu minus f of x, that's the change of f when we go tu from x, and divide that by t. And let the t go to 0, then what we get is really a vector in y, or if it's the real number space, then we get a real number. So it tells us the rate of change when we go in the direction of u. The Gateau derivative and the Frechet derivative are closely tied together, and I'm not going to go through these details and these theorems and these proofs in that way, but you can think of it that in the sense that if we are dealing with regular, normal, non-pathological functions like we usually do, then the directional derivative can be obtained by simply taking the dot product in that direction with the gradient. So because most of the functions we deal with are from Rn to R. So the Frechet derivative takes the place of the gradient. So we have here the gradient, and that kind of explains us what the Frechet derivative is. And then the directional derivative, if we not want the directional derivative, we just take that u and we take the dot product of the gradient with u and we get the Gateau derivative. But this is for the more, I mean, obviously there are pathological functions for which this doesn't apply, but we do not have to deal with those functions in this course. Mostly we're dealing with smooth analytical functions, that there's no problem. Let's see. Here is the matrix representation of the gradient and so forth. So you can come up with this ideas here, and it takes the abstraction level a bit higher as well. One more thing, we can find the derivative of the derivative, meaning the second derivative, and in this case it is pretty much the same thing. We can take the derivative of f prime, which is now, you know, it resides in a higher dimensional space again now because it maps from the real the x space x to the linear functionals. So it becomes a bit more abstract concept, this second derivative. But then the second derivative can be thought of as a bilinear symmetric mapping, you know, and in terms of matrices, we call it the Hessian or the Hessian matrix. And really, there's no need for us to go deeper into more abstract concepts. So basically, we have Rn to R functions that are twice differentiable. Then their second derivative is simply the matrix that you get by taking the second derivatives with respect to across each pairs of variables. So you see why this is symmetric, obviously, at each point, because take the derivative of x1 and x5, for instance, is the same as taking the x5 derivative and then the x1 derivative. So it becomes a symmetric matrix. And then the properties of this Hessian matrix will be basically the topic that we will approach later on this course. And this part here, I'm not going to go into this in the lectures in any more detail or in any more depth. I really do urge you guys to study this on your own. We'll look at this in the exercises, and we'll study this topic in the exercises in the case of Rn to R situation. But taking this abstract thinking a little bit higher up to a little bit higher abstraction level than just basic R to R or Rn to R may help you in formulating a more, how should I say, a more comprehensive image in your mind about what's going on here. But if you're just going to apply this in real valued spaces, then you can think of these spaces as always being Rn and all the functions being from Rn to R. You can pass and even get the maximum grade from this course if you handle that thinking. All right. We are now out of time. I'm going to stop the recording.